Welcome to our fourth video. In this video, the focus is the resolution of vectors into component form. At the end of this video, we hope you can calculate a unit vector for any given vector. Write vectors in I, J and K component form. You notice the I, J and K has three dimensions, I, J and K. Now three-dimensional vectors is really only in the extension 2 course, but I thought I would extend this to some three-dimensional work because I don't think it's a big extension to go from 2 to 3 dimensions, and you'll be able to perform operations with vectors in component form, so including addition, subtraction, multiplication by a scalar. So far we've been doing all our work in 2 dimensions, however vectors do occur of course in 3 dimensions. So I wanted to look at vectors in 3 dimensions. One thing that I should note is that the properties that hold for vectors in 2 dimensions also hold for vectors in 3 dimensions. When the third dimension is introduced and we're graphing them, we introduce a new axis, that's the z-axis. Usually the axes are presented with the x-axis kind of coming forward towards you and the y-axis going to the side and z-axis going up and down representing the vertical component of the vector. This is the most common form of the representation of the axes. However, in some books you do see the x-axis put where the y-axis is. So occasionally you'll see a book where the x-axis is written like this, the y-axis like that, and the z-axis coming straight out, and that gives you your 3 dimensions. But on most occasions the representation is this kind of representation with the x-axis coming out towards us. So using column vector notation with 3 axes, we could say vector A, we would have a third component, so we'd have A1, A2 and A3. If A represented a position vector, it again would have its beginning point at the origin, and the endpoint would represent the points to A1, A2 and A3. For example, if we wanted to graph the vector V and it had coordinates 1, 2 and 3, this would represent 1 unit along the x-axis, 2 units along the y-axis, and to graph the third one you go kind of vertically up, that would be up 3 units on the z-axis. So the representation in 3 dimensions would look like that. Now to look at our vector sum properties, this works in 2 or 3 dimensions. The commutative law says that vector A plus vector B is the same as vector B plus vector A. The associative law means that you can add vectors A plus B first and then add vector C is the same as adding B plus C first and then adding on vector A. The zero vector has the property that any vector plus the zero vector gives you your original vector, and the opposite or inverse law says that if you add a vector to its negative, which you've already looked at geometrically, you will also get the zero vector. And the distributive law says that a number multiplied by 2 vectors can be distributed, so that would be MA plus MB. These properties should be reasonably familiar to you because they work the same as real numbers. One final comment I'd like to make on vector sum properties is that if I was teaching this in a classroom, I would go through and develop an understanding geometrically of these properties rather than just a recall of the properties themselves. We need to develop an understanding of the unit vector. Geometrically, the unit vector is simply, so let's say we have a vector in this direction and it has a magnitude of 3 units. Then the unit vector V would be in the same direction but would only have a magnitude of 1. And we indicate that it's a unit vector by putting a little hat over the top. So this indicates that it is a unit vector in the direction of V. So we'll go through an example of finding the unit vector. Let's say that we have a given vector A which has components 4 and 5. We already know how to find the magnitude of that vector, so that would be the magnitude of this vector is the square root of 16 plus 25, and 16 plus 25 is 41, so we know the magnitude of that vector is root 41. To get the unit vector we need to divide the vector by its magnitude to give you a unit vector. So the unit vector for A is 1 over square root of 41 multiplied by 5. In general, the formula for finding the unit vector would be the unit vector A is found by taking the vector itself and dividing by its magnitude. So we're now ready to look at the resolution of vectors into component form. To begin with, we have a unit vector that's defined as I. Now I is a unit vector along the x-axis, and being a unit vector it has a magnitude of 1. The definition of the unit position vector on the y-axis would be J, and the position unit vector on the z-axis is defined as the vector K. If we were to write these vectors in component form, vector I would be 1 unit on the x-axis and 0 on the y and z-axis. In 2 dimensions, it would simply be written as 1, 0. The vector j would be written as 0 along the x, 1 across the y, and 0 on the z. In 2 dimensions, vector j is just written as 0, 1. And for 3 dimensions, we have the extra unit vector. So vector k would be written as 0, 0, 1. And of course, there is no equivalent in 2 dimensions because there's only 2 dimensions. The thing to note here is that any vector can be written as a sum of the multiples of the components of the I, j, and k vectors. For example, let's define vector v as having the components 3, 2, and 4. Writing that as a sum of its I, j, and k components, we would say that that is 3, 0, 0 plus 0, 2, 0 plus 0, 0, 4. Then we can write this in I, j, and k notation as being 3i, 3 times the vector I, plus 2 times the vector j, plus 4 times the vector k. So this notation here, this I, j, and k notation, resolving a vector into component form, and it is very common for vectors to be written using this notation. Just as a final example, we'll look at, say, a vector in 2 dimensions. So let's say we have a vector defined as vector u equal to minus 4, 5. In I, j, and k notation, that would be 4i plus 5j. We need to look at the magnitude of vectors in this I, j, k notation. I'm going to start with 2 dimensions. So let's imagine we have the vector r that has x lots of the unit vector I and y lots of the unit vector j. So if we were to draw this in our xy plane, it would look like x units, if that's the I vector unit there, and that's the j unit vector there, it would be x lots of the I vector, y lots of the k vector. So this would be x and this would be y. So to find the magnitude of the vector r, we can just simply use Pythagoras theorem, and so again we can say the magnitude of vector r is the square root of x squared plus y squared. Looking at the magnitude of a vector in 3 dimensions, so this time we'll imagine we have a vector that has components xi, yj, and zk. So that would be x units along the x-axis, y units along the j-axis, and z units up on the z-axis. So it would kind of look like that. To find the magnitude of this vector, I kind of want you to imagine the vector being in a box. So I've got this box here, and imagine that vector r going from the origin up to this point up here. So our job is to find the magnitude of that vector there. If you could imagine a line across the base of this box making a right angle with that line there. Here we have a right angle triangle. Remember, the components of r were x, so this is x units long, this is y units long, and z units high. If I just label these points for a minute, so this would be point O, and this is point A, and this is point B, which is a right angle triangle OAB. We'd like to use Pythagoras theorem on this triangle to find the length of the hypotenuse, which is the magnitude of r. We have this side here, z, but we need to find this side here. So on that base on the floor, we can see that that angle there is a right angle, and we use Pythagoras theorem to find the length of OA. So vector OA has magnitude square root of x squared plus y squared. So now we have the magnitude of the two sides of the right angle triangle OAB. So now we can find the magnitude of the vector r. So using Pythagoras theorem in triangle OAB, we can say the magnitude of vector r, and I'm going to square it to make it easier for us. So squaring OA gives us x squared plus y squared, and then adding on the square of the other side, which is z squared. And so we get the magnitude of r is the square root of x squared plus y squared plus z squared, which is really nice because it really is just an extension of the two-dimensional version. So before we start working with vectors in component form, we'll just do a summary of the basic operations with them. Here I've defined two vectors A and B. A has components A1i plus A2j plus A3k, and B has components B1i plus B2j plus B3k. If we were to add these vectors in component form, we could say vector A plus vector B, and we would simply sum their components. So it would be A1 plus B1I plus A2 plus B2J plus A3 plus B3K. Similarly, subtracting the vectors, vector A take away vector B would be A1 minus B1 I plus A2 minus B2J and A3 minus B3K. And finally, multiplying by a scalar, so let's say m is a real number, so I have m times the vector A. Well, again, we just simply multiply out the components, so this would be m A1I plus m A2J plus m A3K. So we covered a lot of new material in this video. Hopefully you've learnt about the unit vector and writing vectors in I, J and K notation, including the application of 3 dimensions, and you've learnt about operations with vectors in component form. In the next video we'll look at doing some examples of questions in component form.